Hi, this is Dr. Remenacker. In this video, we're going to look at how do you take the derivative of the natural log and take a look at some applications of it. Okay, first off, let's get started out with how do you even do the natural log derivative? Well, suppose we start out and define a function, f of x is equal to natural log. That's the same thing as saying y equals ln of x. You've all seen that. That's nothing unusual. Now, using this, if we want to solve for x, we need to apply the inverse of natural log to each side. So to apply the inverse, recall the inverse is e, I can apply e, and e and the natural log will cancel out on the right side, leaving me with x. And on the left side, it leaves me with e raised to the f of x. Actually, keep in mind that could also be written as e to the y equals x because f of x is just a fancy way to say y. Okay, so now that we have this new equation, if we take the derivative of each side, on the right-hand side, the derivative of x is going to give us 1. On the left side, we need to use the chain rule. Well, we've looked at how you compute the chain or the derivative of e raised to some function via the chain rule. And recall, you take the derivative of the outside function, e, which is just going to give you back whatever it was you started with, times the derivative of the inside, which is going to be f prime of x. Next thing we're going to do is we're going to remind ourselves that this e raised to the f of x is nothing more than x. It is? Yeah, if you take a look back up here, see at the top of the screen, e raised to the f of x equals x. So what we can do on this line that we're working with now, we can take this and replace it with x, which gives us x times f prime of x equals 1. If we divide both sides by x, we get f prime of x equals 1 over x. And if you'll recall, looking way back up here, oh yeah, we defined f of x as the natural log of x. So if you take the derivative of the natural log of x, you get 1 over x. That's something you need to remember. Okay, that's going to be used on a regular basis. Okay, so what this brings us to is a theorem. It says for any x greater than 0, and remember you cannot put 0 or negative values into natural log. It's not defined for those. If you have any x value that's greater than 0, the derivative of the natural log is going to be 1 over x. And that's essentially what this theorem is saying. From that, it follows that if we have some coefficient times x, for example, let's say we have something like the natural log of 3x, we should be able to take the derivative of that using the chain rule. Okay, so for example, using the chain rule here, we would take the derivative of natural log. The derivative of the natural log is going to give us 1 divided by c times x. Then the second part of the chain rule says you take the derivative of the inside. Well, the derivative of the inside is going to be c. And notice that we have a c in the numerator times a c in the denominator. Those will cancel. And when they cancel, that leaves us with 1 over x. That's interesting. So as an example, suppose you have something like the derivative of the natural log of 7x. That just winds up being 1 over x. Remember, the 7's cancel. Okay, so the 7's cancel, and it just leaves you with 1 over x. Okay, well, it's not uncommon in mathematics to run into the natural log of the absolute value of x. Yeah, well, we've never really looked at how do you take the derivative of absolute value. Well, it gets a little messy. what winds up happening here, we're going to define this as two separate functions. We're going to take this natural log of absolute value of x and define it as the natural log of x when x is greater than 0. Now, if x is a negative value, what we're going to do is we're going to evaluate the natural log of negative x. The negative here will offset multiplying by the negative x value, getting us back into the range of positive values that natural log can work with. Okay, so if we take the derivative of this first function when x is greater than 0, the derivative of the natural log of x is 1 over x. No big deal. If we take the derivative of the natural log of negative x, this is a situation when x is less than 0, this is going to play out exactly the same as what we had up above here where we did the derivative of the natural log of 7x, remember, and the 7's canceled. The only difference is here our coefficient is a -1. Doesn't matter what it is, it's going to cancel anyway. And if you take the derivative of negative x, you still wind up with 1 over x. Now this is really handy to keep in mind. What this says is if we take the derivative of the natural log of the absolute value of x, okay, if we've got that absolute value in there, it isn't going to affect the outcome. Our result is still going to be 1 over x. That is way worth remembering because you're going to see this. All right, so we've talked a little bit about taking derivatives and we've used letters like c and stuff like that. Let's actually try a couple and see what happens. In this first case, we have 7 times the natural log of x. Two ways you could go about this. You could just write it as 7, the coefficient, times the derivative of the natural log of x, which is 1 over x, and you would get 7 times 1 over x is 7 over x. If you want, and sometimes people are thinking, I don't know if I buy that, Chuck. You know, what happens to the 7? Why don't we do anything with the 7? Well, if you're not comfortable with that direction, try this. Let's treat 7 times natural log of x as the product of two functions f and g. This is going to be the product rule. So with the product rule, recall that's f prime g plus fg prime, and we just go ahead and work it out this way. 7 is the f, the derivative of that is going to be 0. G is the natural log, that's just going to stay natural logs. However, notice this first term, because it's 0 times something, equals 0. Okay, plus, now let's do the second term in the product rule. It says f, well, f is our coefficient. You just bring the coefficient along, times g prime. Oh, g is the function. Oh, so you can see using the product rule that mathematically it is completely legit to say if you have a coefficient, in this case 7, times some function, it's fine to just bring the 7 along times the derivative of the function. Okay, all we're doing is we're saying, you know, the first half of the product rule is going to be 0 anyway, so I'm not going to worry about that. I'm just going to go to the second part where I take that coefficient times the derivative of the function. Now, if you want to revisit that, you're welcome to back the video up and run through that again. Let's take a look at something like this. We have several things going on here. First, notice that we have x cubed times natural log of x. Then we have plus. So we have two things going on. We have two factors being multiplied together. Then we're adding a second term. To take the derivative of the two factors being multiplied together, we need to treat this as a product rule. So the part in orange is going to be differentiated using the product rule. And notice to the right-hand side, I have f prime g plus fg prime. There's nothing wrong with writing that down on your paper, test, quiz, whatever it might be, homework, just to keep track of where you are in the process. After a while, you have done enough of these that you don't need it, and it just works smoothly without writing it down. Okay, so we're going to take the derivative of what's circled in orange. First, we're going to do the derivative of f, which is 3x squared, times g, natural log of x. The second part of the product rule says we're going to do f times g prime. Well, f is just going to be this x cubed. G prime is going to be the 1 over x. And the good news here is we now have the derivative of what is circled in orange. The next thing we're going to do is we're going to compute the derivative of the second term. Well, the derivative of square root of 7 times x is just going to be square root of 7. It's just the coefficient times x to the 0 power, but x to the 0 power is just 1. So we wind up with our square root of 7. And there's that one worked out. Now, you can simplify this. And since we're looking also at higher order derivatives like second derivatives, it's really to your advantage to do some simplification. X cubed times 1 over x, one of the x's will cancel and it gives you this x squared here. So when we clean it up a little bit, we wind up with 3x squared, natural log of x, plus x squared times the square root of 7. So there's the second one worked out. Let's take a look at this next one. On this one, you have two options. One way to do this is with the product rule, as you can see outlined here, and then we're going to come back and use the quotient rule. Well, gosh, Chuck, what's the right way to do this? And the truth is, either is. Either way works fine. So what I'm going to do first is I'm going to use the product rule. In order to use the product rule, I need to rewrite what is circled in orange as the product of two factors. Well, 1 over x squared is really x to the negative 2, and it's going to be times this natural log of absolute value of 3x. Okay, so I've taken a quotient, rewritten it as a product. Now I can use the product rule. And the product rule is going to be applied with x to the negative 2 is f, natural log of the absolute value of 3x as g. And if you'll recall, the natural log of things like the absolute value of 5x or the absolute value of 3x, whatever it is, always works out to be a derivative of 1 over x. Okay, so using the product rule, first thing I'm going to do is take the derivative of this. That means bring the negative 2 out front, subtract 1 from the exponent. There's a negative 2, x to the negative 3. And what I'm going to wind up doing is multiply it by g. Well, that's his natural log of the absolute value of 3x. Then I'm going to multiply by f, well, that's x to the negative 2, times g prime. Well, the derivative of this natural log of the absolute value of 3x is just the 1 over x that you see over here at the far right side. This will clean up some. In the case of this first term, the x to the negative 3 is really in the denominator. So it's going to be a negative 2 natural log absolute value of 3x over x cubed. Then the second term is really 1 over x squared times 1 over x. Well, that's 1 over x cubed. We have a common denominator, which is good news. That means we can add the two fractions together. And when I add them together, it doesn't matter which order I add them in. I can do the minus 2 natural log absolute value of 3x plus 1, or I can do the plus 1 minus the 2 natural log absolute value of 3x, which is what I did over here. That way, the negative, the minus, is in the middle of the expression, and I don't need to concern myself with overlooking a negative that is easily done when it's sitting out front as it was on the left-hand side. Okay, so when we simplify things using the product rule, there's what we get. If we take this exact same function and apply the quotient rule, let's see how that works out for us. Well, using the quotient rule, remember the numerator is going to be f, the denominator is going to be g, and the quotient rule says f prime g, remember it's minus f g prime over g squared. I'm going to do the g squared first. It's easy to forget when you get into all the stuff going on in the numerator. So that's going to be x squared squared. So the denominator is taken care of. Now I'm going to take a look at the numerator. In the numerator, I have f prime. Well, the derivative of this kind of split out is going to be 1 over 3x times 3. You can see that just simplifies to be 1 over x times g. Well, that's this x squared right there, minus. Then we're going to do f, which is the natural log of absolute value of 3x, times the derivative of g. Well, that's 2x. Okay, so what I've done thus far is to use the quotient rule. And I'm going to clean some stuff up here. For example, the 3's will cancel. In this first term, we have x squared divided by this x. X squared over x, as you can see over to the right, is just x. In the second term, I have the natural log of the absolute value of 3x times 2x. All I'm going to do is move this out front like a coefficient, and that's going to give me the second term in the numerator, 2x, natural log absolute value of 3x. The denominator, well, that's just x to the fourth. Okay, so you can see everything's kind of transferred over. In the numerator, notice both terms have a factor of x that can be brought out front. If I factor out the x, okay, so imagine this as being an x factored out, it's going to wind up being the x minus 2x natural log of 3x, and it would have originally been over x to the fourth, but I can cancel an x, and it's going to give me over x cubed. So this winds up then in the end, erase the 1, being 1 minus 2 natural log absolute value of 3x over x cubed. And if we go up a little bit, see in the orange box up at the top right hand side, exact same thing. You can use either technique you want. In some cases, it works out easier to use the product rule. In some cases, it works out easier to use the quotient rule. As you gain more experience, you'll be able to look at the problem and make a good choice on which is the better way to solve it. Okay. One of the things I want you to notice is if you have the natural log of some function. For example, look over to the right-hand side. Let's say y is equal to the natural log of x squared plus 6x minus 3. Inside here is a function referred to as f of x. It doesn't just have to be the variable x. Well, anytime you take the derivative of the natural log that has a function inside or in the argument, it works out using the chain rule that you first do the derivative of natural log, which is going to give us 1 over whatever the function is inside, times, now using the chain rule, you take the derivative of the inside, which is f prime of x. It will always, always, always work out to be the case that you get f prime over f. This is really useful to keep in mind. Okay, if you look in the box on the next line down, anytime you have a function where you have a natural log that you're taking a derivative of and it has a function inside, you can basically look at it and write down what the derivative is going to be. It's going to be f prime over f. Really? Let's try that. and see how it works on a couple of problems. First off, we have the natural log of 2x cubed plus 9x. Well, remember, it's going to be f prime over f. The f is this 2x cubed plus the 9x. The f prime is going to be the derivative of that, 6x squared plus 9. And you know what? It's done. That's all there is to it. In the second example here, we're going to practice this again. We get to do it twice. But the one thing you need to first remember, going back to your properties of natural logs, I'm going to jot it down here, then erase it, is the natural log of m divided by n. Oh yeah, if you have a quotient, is the natural log of whatever's in the numerator minus the natural log of whatever's in the denominator. That's exactly what's written on the top line. We have the natural log of whatever's in the numerator minus the natural log of whatever's in the denominator. And you might be sitting there thinking, really? I'm supposed to remember that? Yep, just like you're supposed to remember 3 times 6 is 18. Okay, these properties with natural logs are going to come into play and save you a lot of work. Now, you could have done the derivative by first writing this as 1 over whatever's inside, is 3x squared plus 6x all over 2x minus 9 times the derivative of this mess, which would require the quotient rule. Oh yeah, this is looking like a lot of fun. You could do it that way and then wade through trying to simplify that. Well, it simplifies considerably if you remember this one property of natural logs. And in fact, at this point, it's easy enough to just look at it and write down what the derivative is. For the first term, the denominator is going to be whatever is in the argument, the inside. The numerator is going to be the derivative of what's inside, the argument. And that one's done. Minus, now for the second one, we're going to have the 2x minus 9 in the denominator, and the derivative is going to be 2. And we're done. Well, get this thing to behave here a bit. My eraser isn't living up to the name of erasing. There it goes. Okay, so there's that one done. Hopefully that makes sense to you. We'd still be using the quotient rule trying to get through the second half of it the other way. This saves a huge amount of time. Okay, let's take a look at an application here. Okay, Skeeter Skateboards buys some online advertising. The number of skateboards sold is related to the amount spent on advertising by the equation n of d is equal to 2,000 plus 175 times the natural log of d. Now, first notice, n of d is going to be the number of skateboards sold. D, be careful, D is the amount of money you spend in hundreds of dollars. What that says is if D is equal to 5, okay, so if we have something like D equals 5, that means we've spent $500. And if we've spent $500, we set D equal to 5. So be careful. That's something that's really easy to overlook and mess up. Okay, part A says how many units are sold when $700 is spent on advertising? First thing we got to be careful of is to remember D is going to be 7. And what we're going to do is we're going to substitute this then into the equation 2,000 plus this 175 natural log of D. And coincidentally, on my calculator, there we go. If you take a look, wow, I've already got the equation in there. What are the odds? Okay, so All I want to do on this first problem is to substitute in 7. So I'm going to go to the table and put in 7 for 700. And what this is going to give us is 2340. How many units are sold? 2,340 skateboards are sold with $700 of advertising. Be careful, don't put down $7 of advertising. Okay, it's really important not to mess up your units. Okay, second question asks us to compute n prime of 10. First, that says take the derivative of our function. Well, the derivative of this function up here, the derivative of the 2000 is 0. So we're going to get n prime of d is going to be 0 plus this 175. The natural log of d, when you compute the derivative, is going to be 1 over d. This basically is just going to work out to be 175 over d. So there's the derivative. Now, you're asked to compute the derivative at 10. So the derivative at 10 is going to be equal to 175 over 10, which is 17.5. Now the question is, well, gosh, what does this mean anyway? I'll see about typing it in here. Make sure I get this in the right color so it'll show up. Good. What this says is, when we go from spending, now be careful because remember we are working in terms of hundreds of dollars, so we put a couple zeros behind it. When we go from spending $1,000 to $1,100, because remember we're increasing by 1 on advertising, the number of skateboards sold increases by 17 units. You're not going to sell half of a skateboard. We're not likely to anyway. Okay, so it doesn't matter if it's 17.8. You're not going to sell 0.8 of a skateboard. So we're actually talking about something physical. This is what's going on. You need to treat the numbers accordingly so it makes some degree of sense as far as what you are selling. Real fair third question. If you want to sell 2,700 skateboards, how much do you have to spend on advertising? This sounds like a realistic question. How much do we need to set aside in marketing for advertising if we've got 2,700 skateboards sitting out there in a warehouse we need to get sold? Okay, so what I'm going to do is use the equation up at the top, and I'm going to set this up as 2,700 because that's the number of skateboards is equal to 2,000 plus 175 ln of d. All right. Subtracting 2,000, we get 700 is equal to 175 ln of d. If we take and we divide both sides by this 175, we wind up with 4 is equal to ln of d. Now, I want to apply the inverse of natural log. Well, the inverse is e. The e and the natural log will cancel, which is going to give me d equals e raised to the 4th. So on my calculator, if I do e to the 4th, okay, This gives us D is equal to 54.598. Now, it's really important to remember this doesn't say we're going to spend $54.60 to get 2,700 skateboards sold. This is in terms of hundreds of dollars. So when we get to the actual dollars, we need to, because it's in terms of hundreds, move the decimal over 2 places. Okay, moving it over 2 places gives us this 5459.8. And essentially, I mean, realistically, if we're working this out in the boardroom, do you really think we're going to say, okay, we'll spend $5,459.80 on advertising? Not likely. I mean, realistically, what's really going to get spent is something like $5,460 or maybe just $5,500. Okay, so realize that while you get numbers decimal and mathematically 5459.8, that's fine mathematically. But when you're actually running the company, I don't even know that you could actually buy $5,459.80 worth of advertising. Or look at you a little bit strange and say, how about we just make that 5,500 bucks and be done with it? So keep in mind that while we are doing solutions mathematically here, you need to adjust those solutions so that they make sense in the real world. Well, I hope this is helpful to you, and I hope you have a good day.